Go. He's on the video now. Energy production. There's primary energy and there's secondary energy. What do you think is the difference? Kenta.
Primary would be when the sun heats up water passively, and secondary when you process that to make energy and electrical.
Mm-hmm. That's correct. So you take energy out of a piece of uranium. That's primary energy. But then if you have to heat water with the uranium and then use the steam to create electricity, that electricity is now secondary energy, right? Burning gasoline is primary. The primary source is heat. But then if you have to use that heat again to create electricity, you're going to get that's secondary energy. Go. Okay. There's something called energy density, and there's specific energy. Turn to the person beside you and decide what you think both of those mean.
Okay. Energy density is the amount of energy in volume. Specific energy is the amount of energy in mass.
You're gonna learn something.
So one of them is energy per volume, one of them is energy per mass. So high energy density is it's like you've got
Aveen,
volume.
I liked what you said. Say what you said.
That was a joke.
No, it was true. You were right.
When something's dense, it has volume.
Oh, that's not what I heard you say. When something's dense, it has volume. Okay. So there's energy per unit mass, and there's energy per unit volume. This is energy density is per unit volume. So it's E per volume. This specific energy, I don't know why they call it this, but this is E per mass. So what would the units of specific energy be? Joules per kilogram. Good. So this is joules per kilogram of stuff. And what would energy density be then?
Joules per meter cubed.
Joules per meter cubed. Meter squared is, that's in another reality. I don't know if they're going to ask you something about specific energy and energy density, but they could. So just so you know the difference, that's what they call them. Yeah, it's in there. Okay, scroll down to this table, and I just want to call to your attention really one number. What number do you think I'm going to call to your attention?
1.10 environment seven.
Nope.
So 1 times 6,000.
It's this one right here. Why do I care about that number? This is nuclear, and hydrogen is the best thing we have after that. So hydrogen's cool, but why don't we just take hydrogen and burn it?
Isn't hydrogen really annoying to get?
It's kind of annoying to get, and there's not very much of it. Anybody know what the atmosphere is mostly made of? Yeah, 80%. Right. And then I think it's is it 20 oxygen?
Something like that.
The hydrogen is quite small.
You can use water.
So you can use water, which is what we do in hydrogen vehicles, right? What you're really doing is splitting the water into hydrogen oxygen, right?
That takes more energy.
And then that takes energy. Right? And you can combine the hydrogen and the oxygen and poof, and you just get water out, which is nice because there's no emissions. But you have to provide electricity in the beginning to split the water into the hydrogen and oxygen. This is 10 to the 5 bigger than hydrogen, right? So 100,000 times more powerful per kilogram of uranium. just like real world thinking, nuclear energy is what's going to save humanity if we are going to be saved. It's not that solar can't be used, it can, and wind energy can be used, and I say like do them all, try them all. But history tells us that until an energy source gets to 20% usage, it doesn't really take off. It takes a long time for an energy source to get up to, like fossil fuels like oil and gas. It took a long time for oil and gas to get up to 20% of our energy use. And then from there it went, took off, right? Because it becomes cheap. And nuclear right now is right at 20% usage. So it's there, and we've perfected a lot of stuff and we've fixed a lot of problems. So obviously there's drawbacks to it, but we're fixing those right now.
What do we do with the waste?
The current reactors that are just about to come online actually run on the waste from other big reactors. So the waste question is being figured out as we speak.
Is there waste from the waste reactors?
Yes, but it's much less and it's not as dangerous.
When we talk about energy density,
Yeah.
about gases, do we, for example, hydrogen, are we talking about like in standard conditions?
Probably not. This is probably in liquid form. Like this is probably liquid hydrogen, LNG. I think. I actually don't know that. I think it would be. Because the energy density of gasoline is much higher. Maybe it is in gaseous form. I don't know actually. That's a good question. We should figure that out. Kenta.
They use nuclear fission instead of fusion right now for most of the energy production.
All of it.
Yeah.
We have no working fusion reactor.
No, they made the experiment work once, right? Just a little.
Yeah.
And then
So we have very recently, we have actually made a net positive fusion reaction, but not a reactor. We're a long way from doing that. The fusion reaction that we got was a very small layer of gold painted on the tip of a diamond. And that was a bunch of lasers.
does fusion have more potential in producing more energy?
Yeah,
But it's just hard.
it's hard.
It's a Lamborghini energy source.
Just
Yes.
bring the sun.
What's nice about fusion is that, like Luke mentioned waste, fusion doesn't have any radioactive waste, right? And it's actually gives you a bigger jump. Like remember that, when we did nuclear, remember that curve that's like this?
Yeah.
And the uranium goes from here to here?
Yeah.
Well, hydrogen to helium goes like boom, it's a big jump, right? So you need less materials, and they're easier materials to handle, right? Hydrogen and helium. But we just haven't done it yet. So you could think maybe in 100 or 200 years, everybody might have a fusion reactor in their house, and you just like, you know, we just use it to like transmutate other things into like donuts and stuff. But right now, fusion's not really a thing.
I think capitalism.
It's cool,
will
though.
allow that.
It's cool.
There will be central power.
You guys understand non-renewable and renewable? Turn to the person beside you and name 2 non-renewable resources and 2 renewable resources.
And then
Anybody got a phone? Can you guys look up for me the current percentage of nuclear
In the world?
Yeah.
I remember we did make 8%.
Well, this says
it's not
6.
10%.
10? Okay.
Worldwide.
Worldwide. How about you? So we're not at
That's
20
according to
yet.
IQ. Pretty trustworthy.
I don't know about this one too. This one's.
Biofuels.
Is that because like a bunch of countries are burning poop or something? Like those French fry grease trucks, there's not very many of them. Yeah.
Does coal count as fossil fuels?
Oh yeah.
This reckons it says over 6%.
Nuclear?
No, for biomass.
Interesting. Maybe other countries are using it more than us. Okay, give me one non-renewable resource.
My brain cells. They're going down at a drastic rate.
Kron? Nuclear is actually a non-renewable resource. That's correct. There is a finite amount. Although, we've got enough to probably go thousands of years. One more non-renewable? Natural gas, sure. So all the ones we're using, oil, natural gas, coal, nuclear, all non-renewable. So we're gonna need something else eventually. But if we got to nuclear, that would fix the greenhouse problem, right? This is the vast majority of what we use is oil, natural gas, and coal. What luxury do we have in this wonderful province of British Columbia? We got lots of water that runs down the mountain. And so we get to use hydroelectric and feel good about ourselves. It's only 2% of global energy production, which is too bad. Yes?
Which category does like wood?
Wood?
Yeah.
They're renewable.
That's biofuel,
Yeah, I guess wood would be biofuel.
but it costs a lot.
Which is not great, yeah.
Very renewable.
Right now we are, as human beings, burning a lot of wood. It breaks my heart on many levels actually because in Brazil right now, the current government is really pro beef ranches, and so you just mow down all the trees in those Amazon plateaus, and then you have your cattle ranch. So it's like you're getting rid of the trees. Why is that bad? Because trees are really our only carbon capture device that we have that's working well. So you get rid of the capturing the carbon, and then you burn the trees, which breaks my heart on the level of a woodworker. I'm a woodworker. I don't know if you guys know that, but it's beautiful wood. It's like mahogany. You can make the most beautiful furniture out of it, but just burn it. Make room. And then we're raising beef so people can eat the beef, and that methane, and it's all bad. It's all bad. Give me a renewable source.
Sun.
Wind, sun, hydro. These are all. Nuclear fusion would be renewable too. Geothermal is a pretty good one. Geothermal is troublesome though, because what you have to realize is that you're taking heat out of the inside of the planet, putting it in the atmosphere. So we really need to be doing the reverse, right? So I feel like geothermal is a great idea. I think we should have it go both ways. Like if you're living in somewhere hot like Nevada, you should be running air conditioners, taking the heat in your house and putting it back in the ground, right? Okay, so that's the percentage global stuff, global perspective we're having here. Fossil fuels, da-da-da. This is the basic coal burning power plant. This is most of the electricity that we generate in the world is done like this. You conveyor belt the coal in there. It used to be a guy literally just shoveling the coal. And you drop it in there and you burn it in a big furnace. And you have this heat exchanger, like a radiator in a car. It's just a pipe that goes up and down with water in it. And they heat it up, right? And that water gets hot and it turns into steam. And the steam goes through and turns a turbine. Did I show you guys the pop can with the bowl and it go like this?
Yeah.
That's essentially what's powering this. People get it wrong sometimes. We like to think, well, we get the steam and the steam goes up and it's like, and it rises up. It's not really that. It's really here that the power is created. So when the steam drops through here, it condenses in a condenser. And when it condenses, what is left? When water vapor condenses into water,
Yeah.
nothing. You have a vacuum, right? And what happens when there's a vacuum? It's pressure. So it's really the air pressure of the atmosphere that drives this thing. Because when this steam condenses, a vacuum is left and it pulls the air down. This is how a steam engine actually works too. And it pulls that, it twists that turbine, right? And then when we twist the turbine, we have some coils of wire in here. And when you spin a coil of wire, what do you get? You're gonna get a current, an inducted current in there, right? And so it goes out. Does it just go out?
No, it comes back.
Right, it goes out for this part of the spin, and then it comes back for the other part of the spin, and then it goes out, and then it comes back. So do electrons actually move from the power plant to us? No, they just move back and forth. But that energy gets to us. Always energy things.
So do we like put extra energy in the system to condense them, like cool water down?
No.
How does it cool down?
It just cools. It's like when I take that pop can and I put it in the cold water.
Oh, because it's
Comes
not
back to
heated
cold.
anymore.
Yeah. This is cold, and actually, that's a good point. So one side effect of this is that you have to have this water condense. So you have to have it come back to a cold state. And so what we do is we run river water through here to cool it, right? So that's a great side effect. We heat up the river water as well. It's a really nice thing to do for the fish and everything. But there is in the Western world, there are limitations on how much you can heat the river. You're allowed to heat it, but only so much.
I just wanted to ask.
Yeah.
If it's producing an AC current.
Yeah.
And current makes magnetic field. Does that mean that the field is just going like?
So if you think of the wire,
Mm-hmm.
the field is going like this, like that,
Oh.
like this, and then like that. And if nothing else is around, that doesn't matter. It doesn't take any energy. It's just a field. But there was a guy in northern BC who, on his farm, they put the big transmission lines over his farm. And so he built a barn underneath the transmission lines, and he set up a bunch of long wires, coils, and he pulled electricity out of the transmission lines. And he ran his farm off of it.
And this is illegal? This is ingenious.
Well, it was a question. It went to court, actually. Hydro was like, he's stealing our power, and he was like, I haven't hooked up to the line. You guys built the thing over my farm. And I actually don't know how it turned out, but it went quite a ways.
I'll do some research.
Yeah, okay.
Dude.
Okay, so power plant makes power. We run everything on electricity. Eric?
Why can't we use like human to generate electricity? Use
Whoa, whoa, whoa. Whoa.
It's like when you buy it.
Just,
you can-
let's, everybody, just,
That was satire.
cut it off! Cut it off.
No, like you're spinning the. Like, when you're buying, like you're spinning the.
No, the thing is.
Oh, I see what you mean, yeah.
Yeah.
Let's be clear, you're not talking about burning humans in the forest, right?
Use human to.
That's what I thought you
buy
meant.
a pedal to
No,
spin
the
a
thing
turbine.
is, you need
Yeah.
to still input energy into the humans through food, and you have to produce that food somewhere or another. It's not as efficient. You can't mass
Eric,
produce.
it's interesting because I have this video that I play to my grade 10s and sometimes my 11s. There was an energy production symposium done in Amsterdam a few years back. And these university students, they were architects. They made this super nice graphic presentation, and it was gonna be like, because if you've ever been to Amsterdam, there's bikes everywhere. You go to the train station, there's thousands of bicycles, and everybody gets around that way, you know? It's kind of awesome. And they said, all these people are biking around the city, We're gonna make bikes that store the energy from pedaling, and then when you get home, you plug it into this rack, you know, and it'll like light the street lights and give power to the homes and everything. This will not work. You tell me.
That energy is used to get you to move.
The energy gets used up moving you across the city.
Yes, but if you're using like stationary bikes,
Sure.
yeah.
Trees?
If you can get people to sit and pedal for
Like for
Like,
all
all day long.
prisoners, like you paddle to
Wait. This is from Rick and Morty. I saw this episode. I saw that.
You just
Create a mini universe, huh?
choose your.
Eric, there's a movie about what you're talking about. It's called The Matrix.
Wait,
Where are they making it?
Plug people into the Matrix and just
how is it used to try?
everybody's sitting in there.
It's Eric. It's free. How do we
Uh,
reverse?
actually, Eric, we did a calculation of it. It's not very much. It comes out to not that much energy, but if you had enough people, you could.
How is it used to transport you across? Because the world or the bikes that Amsterdam thing, how is it used? If it's
Well,
not
we
like a-
don't have friction-free bicycles, right?
But if it's directly inputted towards a battery.
Step one, friction.
Okay, but so Luke is asking a good question. He's saying why, like, if we're riding the bike anyway, why don't we just use we're riding across the city, so just take that energy and store it in the battery. But I know this and Jake knows this. If you start to store your energy in the battery, it becomes a lot harder to pedal.
I know, you just get really big legs.
We have found the answer. Just get really big legs. That's gonna be my life motto from now on. Don't skip leg day.
Yeah.
Right?
Make the people healthier.
This is called a Sankey diagram. Everyone say Sankey diagram. I like the name, but you start off with 100 units of energy. Maybe it's joules, whatever it is. 100%, we'll say. And if this is a coal-fired power plant, this is all potential energy stored in the coal. By the way, where does the energy come from in the coal? How did it get there?
Chemical bonds.
Did you just say bodies?
Bonds. Like when you burn coal, you break the chemical bonds.
Oh, bonds.
Yeah.
Good. Yeah, okay, that's better than bonds. Well, I'm getting a dark Freudian thing from Eric here. Yeah, you're right. It's in the bonds, but how did that energy get in the bonds? Allison? Anaerobic decay? Okay. Yeah, when it decays, it becomes coal, but before that, what was it? Yeah, mostly plants, right? So how did the energy get into the plant?
The sun.
Photosynthesis, the sun, right? So it's really solar energy, so don't worry about it. You'll notice that there are 10 squares here. So each square is how many percent? 10%. So you'll see right here, 20% has disappeared. Where did it go?
Boiler.
I don't know what it says down there.
It says boiler.
Boiler? Okay, 20%'s gone to the boiler. So you lose that much energy. So how much do we have left? So right here is 80%. Now we got 80% left. And then how much gets used up in the condenser? 40. And so we have 40% left, right? And then 5% gets used up in the generator, the turbine, and what are we left with?
35% out.
35%. It's kind of a nice way to visualize it, right?
I thought we didn't put energy for the boiler.
Yeah, you said you didn't put energy in.
We don't put energy in, that's energy coming out. This is heat that comes out of the boiler that we never get.
Oh, that's true now. I get it.
Yeah. And same as the condenser. There's a lot of heat there that just leaks out to the environment, right? So you start here and you go here and you go here and you go here and you go here. It's just kind of a nice visualization of your energy going tick, 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 tick. So obviously, the more efficient, the better. And if you have a Sankey diagram that ends in a wider final energy, you're better off. So that's how a Sankey diagram works. And you can calculate the efficiency and blah, 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 blah. You guys can probably do all those kind of problems fairly easily.
Will we ever be able to reach 100% efficiency? I don't mean like in the next 100 years, like in theoretical.
Maybe, but I don't think you need to.
It's not perpetual energy.
It's hard. It's really difficult to get 100. You can get close. You can get close.
Well, if you make like a machine that's like is close to 100% efficient, then you account for that by having a design where it's like it can work with a little less power.
Yeah, that's right. Nuclear, I think, is really good for you guys to know and understand. So it comes down to the fact that radioactive stuff gets hot. Why does it get hot? Because of radioactive decay. What kind of process are we talking about? Fission or fusion? It's fission. We don't know how to do fusion well yet. So this is fission, and you have some fuel in here. Let me blow this up a little bit. And there are a bunch of different designs. This is kind of the pressurized water reactor is pretty common. So you have these fuel rods, and they would have U-235 probably. And then you have to have a moderator in here. So this block would be made of either graphite or water, probably. Coming up with different moderators, but why do we need a moderator? Kenta.
To slow down the uranium-235 so they can absorb each other.
Ooh, Allison?
Stop with the chain reaction and have it
Nope.
Isn't it just so that it doesn't leak radiation?
Nope.
If
I'm
it-
glad we're learning this.
It's to slow down. Like you use the 235.
It is to slow down. To slow down what?
The U-235. No, it's like that.
Ah.
neutrons, yeah.
Okay.
So
So, repeat this to the person beside you. The moderator is to slow down the neutrons.
Wait, why does the moderator have to be graphite or water? What's why?
It doesn't have to be. It's just that they work and they're easy to find and get.
Like, why do they work? What makes them slow down?
So the moderator is like, it's not, the moderator gets confused. It's confusion, right? Easy potential confusion. Because that word moderator, it makes you think that the moderator is like moderating the reaction. This is not the case. The moderator is actually allowing the reaction to occur. Do you remember me telling you about my dad and me and our guns? And my dad had the really powerful gun with the small bullet. And when it hit the stump, the log, what happened?
Went straight through.
Right through. So put your hands like this. This is a uranium atom. It's going like this. Do that. If you shoot a bullet fast through it, what's going to happen? It's just going to go like this, right? The hole is going to go through and it's just going to seal up again. What about something slow? It's going to go. And then you have two, right? So we have to slow down the neutrons enough so that it spends enough time going through the uranium atom, the nucleus, that it actually splits the nucleus. Make sense? Okay, I'm gonna pause the video here because I know it'll be too long for me to upload. And I'm gonna start the next video with the same thing.